So I'm very happy today. Actually, 2 years ago I had my last students defending on Good Friday. So today is an even better Friday. We have two students defending. The first one is Sara Lapan, who will defend her thesis on the existence of attracting domains for maps tangent to the identity.
Thank you. Welcome, and thank you for coming today. Especially want to thank my advisor and my committee members. Since there's a wide range of audience here, I'm going to start out slow and give like a general idea of what dynamics is, and then I'll build up to getting to my own research. Okay, so first of all, well, what's a dynamical system? Well, imagine a pool table, and you have one ball and a cue stick, and you put the ball on the table, and you take note of the spot that you put it on, and then you hit the ball with your cue stick at a particular angle with a particular force. And then the ball will move around the table, and it eventually stops. And then you take note of its new location, and you hit it again at the exact same angle with the exact same force. And again, it'll move around the table and eventually stop. And you keep repeating this process. So this is studying the various positions that the ball can attain given this system. So the space that we have is the pool table, and the function that we're iterating is how we're hitting the ball. So you can have different things arise. You can have a spot where the ball is positioned where it never actually moves. So maybe somewhere along the wall, the way you're hitting it, it just gets stuck there and it doesn't move anywhere. So you could have a fixed point. Or maybe you could have it in a location where you hit it, and after, say, hitting it 5 times, it winds up exactly where it started. So you can have like a periodic point of the system. Or maybe you hit it and it gets close to the fixed point, but it never actually reaches it. And so it just gets closer and closer. So you could have maybe, I don't know if this happens in pool, but you could have it getting closer and closer to that point. Or maybe you hit the ball and it does what it's actually supposed to, and it goes through one of the holes. And then it has left the system, and we can no longer say how this function would act on it. Okay, so that's in general what a dynamical system is, hands-on. So now what is a holomorphic dynamical system? So let F be a map from U to Cm, a holomorphic map, where U is an open subset of Cm, and F fixes a point P in U. So this is called a discrete holomorphic local dynamical system. So for those of you who don't know what holomorphic means, every time I say it, just think of a polynomial in complex variables. They'll be pretty much there for this talk. Okay. And the set of discrete holomorphic local dynamical systems at P, we're going to refer to as end CMP. So the nth iterate of the function f, this is denoted by f to the n, and it's f composed with itself n times. And the nth iterate of a point in U is denoted by z sub n, and this is the n, f to the n of z. So f, that's our function, like hitting like the cue stick action. And we keep iterating it. And the discrete comes from, well, we're hitting it like 1, 2, 3 times, and not a spectrum of times. So, and then local, well, we're just going to be studying points that are very close to P, not a big space. So it's not going to be all Cm, just close to P. Okay, so we have a couple guiding questions for this talk, and they're also kind of some of the guiding questions of studying dynamics. So first of all, can we express f in a simpler form? So if we could express it in a simpler form, it would be easier to understand the dynamics of the system. So in particular, is f holomorphically conjugate to a simpler looking map? And then the dynamics of the conjugation would be the same as f. So if we're conjugating by phi, so phi of f, a phi inverse. The nth iterate of this is just the same thing as phi of f to the n, a phi inverse. So that's why we can study the conjugation instead of the original map. Okay, and 2, what happens to points near the fixed point P upon iteration by f? And in particular, we're going to be looking at if points are going to be attracted to the fixed point when we apply the map, and if so, if they're attracted along a particular direction. Okay, so in particular, we're going to be studying maps that are tangent to the identity. So from now on, assume that P is the fixed point is actually at the origin, and we also want to assume that F is nonlinear. So let F and N CM0 be defined on U. So since it's holomorphic near the origin, we can express it like this, where so F of Z equals P1Z plus PKZ plus PK plus 1Z plus higher order terms, where each of these Pj is a homogeneous polynomial of degree j. And we're assuming Pk is non-zero, so it's the first non-zero term after the linear term. And we're going to say that k is the order of f at the origin. So k has to have degree at least 2. Okay, so definition, f is called tangent to the identity if p1 of z equals z. So if the linear term is the identity map. And that's the type of map that we're going to be studying today. So from now on, assume f is tangent to the identity of order k at the origin. Okay, so before we move on to higher dimensions, let's just look at what happens in dimension 1. So here's an example, and we want to know what happens to points near the origin under iteration. So we have the map f of z equals z minus z squared, so it's order 2, and we can express it like z times 1 minus z. So if z is small and positive, then the 1 minus z is going to be less than 1, but positive, so z1, the iterative of z is going to be smaller in size, and when we keep applying the map, then it's going to be shrinking in size, and so the iterate zn is going to go to 0. But if z is less than 0, then 1 minus z is going to have absolute value greater than 1, or it's also just greater than 1. So it's going to be growing in size, and so zn is going to negative infinity. So here on the left we have a local picture of what's going on, and so here this is the real line, and so over here this is the positive real, and we said that if z is small and positive, then it's going to be going this direction towards the origin, and on the other side it's going to be moving away off to negative infinity, but I have written up the inverse map, which behaves symmetrically. Okay, and we'll talk more in a minute about where these pictures actually come from. The picture on the right is what's happening more globally. So this is all the points, so the interior of it is all the points that are bounded under iteration by this map. And I'll refer to this at the end of the talk, but so it's like the cauliflower set. That's what the C stands for. So it looks like cauliflower. So the points are all attracted to 0. And so this picture over here kind of sits inside there. It's hard not to shade this, but so the local picture is just a very small subset of that. Okay, so this leads into a very interesting theorem in one-dimensional dynamics. So let's let f and n c0 be tangent to the identity of order k. So near the origin, we can express f like this. So z times 1 plus akz to the k minus 1 plus higher order terms. And again, we're assuming ak is non-zero. And so we get that there are k minus 1 attracting directions, and similarly for repelling directions. And this is coming from when akz to the k minus 1 is real and small and negative, then we're going to be shrinking in size, just like in the other example, and when it's positive, then it'll be growing in absolute value. Okay. And so we saw this picture before, but here we have, this is an attracting direction, so it's the map z times 1 minus z squared. So we have 2 attracting directions, there and there, and then 2 repelling directions, there and there. Okay, so the Lofa-2 flower theorem. So each of these attracting directions has an attracting petal that's centered along it, and the union of these petals forms a neighborhood of the origin. And so that's what these pictures are really representing. So we have this, so this is the direction, and then the whole petal is centered along it. Okay, and then secondly, there exists an injective holomorphic map, phi, from the petal P to C, such that image contains a right half plane, and when you conjugate it, it's conjugate to translation. So this first question, or this first statement is answering like our second guiding question: what do we know about points being attracted to the origin? And the second one is answering our first question: can we simplify how f looks? So if I draw a picture, let's just look at the one on the left. Okay, so we have this petal here, and f is mapping the petal into itself. And then we have our map phi, and it's mapping it to something that looks like that. So it's the whole right half, or it contains a whole right half plane. So it goes off to infinity. And we're mapping this point 0 off to infinity. And then on the space, we know z is going to be mapping to z plus 1. So it's just translation every time we iterate. Okay, so what we want to do in higher dimensions is we want to be able to come up with something that generalizes this idea. So assume f is an NCM0 and is tangent to the identity of order k. So again, we can express f like this: z plus pk plus higher order terms. And we come up with, so characteristic directions are in some way analogous to the attracting and repelling directions of the dimension 1 case. They're not defined in the same way, but they have similar idea. So if v is in Cm minus 0, such that pk of v equals alpha v for some alpha in C, then the projection of v into the projective space is a characteristic direction of f. And v is non-degenerate if alpha is non-zero, and it's degenerate if alpha equals 0. So other than that, we don't care about the specific value of alpha. Okay, so where is this definition coming from, or why should we care about it? So if f were just of the form identity plus pk, and we didn't have any higher order terms, then this v would be a fixed point, or we're fixing this ray for looking in Cm. So we know that points are going to be staying on that line, although they may be moving around. So it tells us a little bit, it tells us that maybe it's a good place to start. And they end up being very important. So suppose v is a non-degenerate characteristic direction of f, and v has m minus 1, but then v has m minus 1 constants in C associated to it, and these constants are called the directors of f at v. So the formula for it comes from the pk term, but I didn't think it was helpful to write down. So just, there are m minus 1 constants. And these actually are very important in the dynamics. So we have a big theorem in m dimensions by Hakim. So let f in NCM0 have characteristic direction v. Suppose v is non-degenerate, and the real part of the directors are all strictly positive. Then f satisfies the following local property. 1, there exists a domain omega that's invariant under f, and whose points are attracted to the origin tangentially to the direction v. And secondly, f on omega is conjugate to translation via an injective holomorphic map phi from omega to Cm. And in particular, we can write out that I'm doing translation in the last coordinate, and everything else is the identity in our new space. So you can kind of picture, since I can't draw in Cm, you can kind of picture the same thing going on here. So we're doing mapping over here to get conjugacy to translation. Okay, and then furthermore, if f is an automorphism of Cm, then we can say f satisfies a more global property. And so there exists an invariant domain, as in our local property, that is biholomorphic to Cm via phi, and f is conjugate to translation again on that domain. Okay, so remember our assumptions in the previous theorem were that v is non-degenerate and that the directors are all strictly positive. So here we have another theorem from Hakim, suppose V is a non-degenerate characteristic direction of F. If there exists a domain where all orbits converge to the origin tangentially to the direction V, then the directors of V have non-negative real part. So this tells us if we have any directors that have negative real part, then we can't have an attracting domain along that direction. But what's left open is what happens when some or all of the directors have real part equal to 0. And that's what I've spent most of my time studying. So suppose F is an NC2, 0, and has only one characteristic direction, and that direction is also non-degenerate. Well, it turns out that the director of V must be 0. So one thing I wanted to mention is, so the number of characteristic directions depends on the order of F and also the dimension. So for dimension M and order K, it's K to the power minus 1 over K minus 1. So, or they're infinitely many. So in this case, all of those are the same direction. Okay, so then we have one of the main results of my thesis. Let F and NC2 have characteristic direction V. Suppose V is non-degenerate, and V is the only characteristic direction of F. Then we get the same conclusion as in Hakim's theorem. So we have this local property where there exists an invariant domain whose points are attracted to the origin tangentially to V. And 2, F is conjugate to translation on that domain. And finally, if F is an automorphism, then F satisfies the global property that domain can be bihomorphic to C2, and again, F is acting like translation on our new domain. Okay, so I'm going to go over a brief outline of the proof, but before I do that, I wanted to mention that Liz Vivas also works in this area, and around the same time, she was studying irregular characteristic directions, and it turns out that given the assumptions on F, that V has to be in a regular direction, and then she also proved the same result for irregular directions. Okay, so the steps of the proof. 1, so we first want to simplify F using a linear change of coordinates. So by change of coordinates, I mean that we have, well, we're able to conjugate. So we have phi has an inverse, so it's injective. And so we're going to talk about changes of coordinates a lot in general. But first, we're starting out with a linear one. And then second step, we're going to construct 3 coordinate changes in order to holomorphically conjugate F to translation. And then finally, we're going to assume F is an automorphism and show how to extend this to the global result. Okay, so you can just trust me that given our assumptions on F, that F is linearly conjugate to this map. So just looking at the top coordinate, we have Z is mapping to Z times 1 plus ZW RZW minus W to the K minus 1 plus P of ZW. So this ZWR has the same degree as the W to the K minus 1. So they both have degree K minus 1 here. And P is degree like K plus 1 or higher terms. Those are power series. And then the W coordinate looks pretty much the same, except we have this Z to the K term in here. And again, Q is going to be analogous to P, so it's terms of degree greater than or equal to K plus 1. And for this map, 0, 1 is the unique characteristic direction. Okay, so to simplify things for this talk, I'm going to assume that F is of this form in 1, and that K equals 2, which means we don't have the R term, and we don't have any higher order terms, so it simplifies to this much nicer looking map. But the steps are exactly the same, just a little less messy. Okay, so step 2, our first coordinate change. So we're going to map, so psi 1 is a map from ZW to our new coordinates UV, and it's going to be W over Z squared, comma 1 over W. So the reason we're doing this is we're ascending, the origin was the fixed point in the previous map, and we're sending the origin off to infinity. And we're also in this, so 1 over w, if that goes to 0, if w goes to 0, then 1 over w has to go to infinity. And if w over z squared, or just w over z, goes to infinity, that means our z over w is going to 0. And so writing this out, so we wanted this to go to 0, 0 along the direction 0, 1. And so that would mean that we want Zn, Wn to go to 0, 1. So that's, if we wrote it, Zn over Wn colon 1. So these are the same thing if we divide by Wn, assuming it's not 0. So that's why, so if we want Zn over Wm to go to 0 if it's going along that direction, which means W over Z is going to infinity. Okay, and then, well, I'll say in a moment where this is defined, where the inverse is defined, but psi inverse, or psi1 inverse, is going to map uv back to our original coordinates by this map, 1 over v squared of u, comma 1 over v. Okay, so fix some r, some large r, and some small delta greater than 0, and theta between 0 and pi over 4. So let omega be, let's see, is going to be uv, where the real part of u is greater than r. We have u to the 3/2 is less than delta v. Argu, we're bounding the argument of u and v. So argu is less than theta, and arg is less than theta over 2. Alright, so I'm going to draw a picture of that. So if we fix v, then we can draw what u looks like. This is the real axis. This is the imaginary axis. And so we have, this is our r. And then we have that, well, u is going to be less than delta v to the 2/3. So that gives us a circular bound. So u is less than delta v to the 2/3. And then we have the argument is less than theta. So this is the area, this is the region that u is defined in for a fixed v. Okay, and then, so we can do the same, thing. So if we fix u instead, then we can draw what v is. Sorry. Okay. So we're bounding v from below, so the same bound is here. So again, we get a circular bound. And then we have the argument of v is less than theta over 2. So this is where v is going to be, and this domain extends all the way there, off to infinity. Okay, so that's where we're working in. Okay, so then this map psi1 is a biholomorphism from, well, psi1 inverse of omega 1 to omega 1. This was omega 1. Okay, so let f1 equals psi1 of f of psi1 inverse. Then we can write how f, or f1, is acting on our new coordinates. And so it's going to send, so remember this is the first iterate, the subscript 1 denotes first iterate. So u1 equals u plus 2 over v plus terms of order 1 over v squared. So since v is large, these are very small terms. And v1 equals v plus 1 plus o of 1 over u comma 1 over v. So using the definition of omega 1 and these expressions for u1 and v1, we can just automatically, or we can, it's straightforward to show that f of omega 1 is in omega 1. So omega 1 is f invariant. And on omega 1, Vn is very roughly like v plus n, and un is similarly for u plus 2 log n. So that if we totally ignored those terms, then Vn would equal V plus n. And again, if we ignored this and assumed V was Vn, or was n, then that's where we get these approximations. Okay. So for the second coordinate change, what we want to do is just work with our second coordinate. We want to make that conjugate to translation. Or it's called a Fatu coordinate, if we can get this. Tau of f equals tau plus 1. So our naive approach would just be to say that tau is, the limit as n goes to infinity of Vn minus n, because then we would have already that equation, tau of f equals tau plus 1. However, this limit does not converge, so we have to do a little bit more work. So let phi naught and phi 1 be holomorphic maps from the projection of omega 1 to the u coordinate. So it's like here. And define t of uv to be v times 1 plus phi naught of u plus phi 1 of u over v. So we're going to define these phi naughts and phi 1 so that they do what we want. So then t1, when f is acting on our new coordinate t, we get t1 equals t plus 1 plus, then we have terms that only involve u, phi naught, and phi naught prime. And we have then plus 1 over v, and terms that only involve u, phi naught prime, phi 1, and phi 1 prime. So a and b only depend on u. And then we have terms of order 1 over v squared. So those are small. So the key idea here is to define phi naught by setting a equal to 0 and solving this differential equation so that we can get rid of that a term altogether, and doing the same thing to eliminate the b term. So setting b equal to 0, and then now that we have phi naught, we can define what phi 1 is going to be. So this was, so people had done like one differential equation before, but this was a little bit a different technique. Okay, so now we can define our tau, which is what we wanted our coordinate to be, and it's going to be the limit as n goes to infinity of Tn minus n. So then our second coordinate change, try to, maps uv to u tau. It's only changing the second coordinate, and we'll let f2 be how f acts on our new coordinates. So then it sends u1 to u plus 2 over tau, plus 2 phi naught of u over tau, and then plus these smaller terms. So u was roughly like log n, and tau is roughly n. So this is going to be very small. And then we have tau 1 equals tau plus 1. So we're done with the second coordinate. And there is a domain omega 2 that we define in a very similar way to omega 1, and on which psi 2 inverse is a biholomorphism onto its image. So we do the same process there. Alright, so now we have our final coordinate change. And so we want our first coordinate to look like the identity. So we have, so naively we could say sigma equals the limit as n goes to infinity of un, because then we would have already that psi of, or sigma of f equals sigma. But again, this limit fails to converge, so we have to do a little bit more work. So let alpha be, so pi 1 is projection onto the first coordinate of omega 2 to c, so that's holomorphic, and we define s, so this is similar to how we define t and sigma, or t and tau. So define s of u tau to be u minus 2 log tau plus alpha of u. So what we're doing with this s, well, we want to get rid of this 2 over tau term, and so we can get rid of that and only get in like very small terms by adding in this minus 2 log tau. And then we're going to define alpha of u so that we can get rid of this term and only have very small terms in the end. So then we have s1 equals s plus terms of order 1 over u to the 3/2 tau. And so this is roughly log 1 over log n to the 3/2 n. So now we have, well, that sum is going to be finite, so we can have sigma defined as the limit as n goes to infinity of Sn, and now this limit converges. So our final coordinate change is sending u tau to sigma tau, and we'll let f3 be how f acts on our new coordinates, and now this is exactly what we wanted to get in the end. So we have sigma 1 tau 1 is getting mapped to sigma comma tau plus 1. And again, we need to find a domain on which psi 3 inverse is a bihomomorphism onto its image, and that is invariant under F3. Okay, so this is summarizing what we just did in case we got lost. So capital psi is just all of the transformations, all of the changes of coordinate put together. And omega is the inverse, is omega 3 moved back to our original coordinate ZW. So we have our original coordinates mapped themselves under F, and then we have psi is a bihomomorphism from omega to omega 3, and then down here we have F3 is acting on sigma tau by translation. Okay, so that is a conclusion for the local property. Okay, and then, well, we want to talk about the global result, but we're not going to spend too much time on that. So assume F is an automorphism, and let pi equal the union of F to the negative n of omega. So we're looking at all the things that eventually get mapped to omega. And we can extend the domain of psi to pi by defining psi of zw to be psi of zn wn minus 0 comma n. And so this is, if zw is not in omega, then, well, it wasn't already defined, but for some iterate, for some m, zm is in omega, and then we're defining it there. And, well, all m greater than that too, it's in omega. And this is well defined. And then on pi, we have that f-axis translation, so psi of f equals psi plus 0 comma 1. And so using standard techniques that were also used by Ueda, Weikert, and many other people, we can show that this is a bihomomorphism, but I'm not going to go into those steps. So therefore we have the global property is satisfied. Okay, so we finished with the theorem. So can you recall what our guiding questions were? So can f be expressed in a simpler form? And what happens to points near the fixed point under iteration by f? Okay, so that was our general search. So we just addressed these questions for this map that has a unique characteristic direction, and that direction is non-degenerate. So now we're briefly going to address these questions for 4 different types of maps, and several of them are of the form x times 1 minus x in the first coordinate. So for the rest of the talk, let C be this basin of attraction. So is that cauliflower set at the beginning, everything inside it. Should I end it here, or should I go through the slides?
I guess you can go off for a few minutes.
Okay, so we have our first example. So again, remember, we need the director, or the real part of it, to be equal to 0. Otherwise, it would be covered by the other theorems. So this example is also in Reeves' thesis. So for alpha in R minus 0, the map, we have x times 1 minus x, and y times 1 minus 1 plus I alpha x. And this has non-degenerate characteristic direction 1, 0, and director I alpha. So it has the real part of 0. So then xn is going to 0 if and only if x is in that cauliflower set, and yn goes to 0. So we can show that yn goes to 0 if x is in that set. And so we know that C cross, we know that
cauliflower cross conflict.
Cauliflower cross C is attracted to the origin, but its points excluding the cauliflower cross 0 do not converge tangentially to 1, 0. So we have a domain of attraction that exists, but it's not converging along the direction. Okay, then we have the second example. So this is dimension 3 now. And we'll have one of the directors is 0. So again, in the first coordinate, we have x times 1 minus x. Then we have y times 1 minus x and z times 1 minus 2x. So again, this has, well, it has 1, 0, 0 as our non-degenerate characteristic direction. And this is going to have directors 0 and 1. So since the director is 0, we don't a priori know what's going to happen. But again, we know the first coordinate, the xn goes to 0, if and only if it's in that cauliflower set. And yn, zn, and zn over xn also go to 0 if x is in that set. So it takes a little bit of writing out to show that. But then we know from this that x, y, and z, if they're in the cauliflower set cross C2, then as n goes to infinity, the point is going to go to the origin. However, it's not going to go to the origin along our direction 1, 0, 0 unless y equals 0. So so again, this is attracted to the origin, but not along the direction that we were wanting. Okay, and then example 3, dimension 3, and we have both directors equal 0. So I think it's easier if I just point out the differences in this map. So we have this AY and AY are the same, but the y term has a different coefficient. And the same thing here, these two z's have the same coefficient, but this one is different. And all of them are in C. So this map then has 1, 0, 0 as a non-degenerate characteristic direction, and both of its directors are going to be 0. So in this case, this is our first positive result from these examples. We can show that there exists an invariant attracting domain whose points converge to the origin, and they're actually converging along the direction of 1, 0, 0. But I'm still working on showing if it's going to be conjugate to translation. Okay, and then our final example. So again, in dimension 3, and both directors equal 0. So we have our favorite first coordinate, x times 1 minus x. And then we have here y times 1 minus x minus y. And then z times 1 minus x plus y. So the main difference here, this is the minus and plus there. So this again has 1, 0, 0 as a non-degenerate characteristic direction, but both of its directors are 0. So suppose you have a point that's converging to the origin, but none of the points ever actually reach 0. Then we have yn over xn and zn over xn, so those come about in the same way that we got these here. So if it's going to go along 1, 0, 0, then we need yn over xn to go to the 0 and zn over xn to go to 0. But we can't have both of them go to 0 since, well, this whole term can never be 0, and well, we have a minus there and a plus there. So there does not exist an invariant attracting domain whose points converge along that direction. Okay, so conclusion. So to summarize, in my thesis I showed that for f in NC2, 0, that has a unique characteristic direction, and that direction is non-degenerate. Then there exists an invariant attracting domain whose points converge along a particular direction, so the same direction, and is conjugate to translation. And then we can have the more global result. If f is an automorphism, then our domain of attraction is actually isomorphic to C2, or of a 2-Gubov domain. And in addition, we talked about a few examples of different maps in dimension 2 and 3 that Hakim's theorem and my theorem don't apply to. So we have directors equal 0 in them. And in some of the cases, we had an invariant attracting domain that converged along a direction, and in some cases we did not.
All right, thanks. All right, so are there any questions from the committee? could ask, like, maybe I could ask, I mean, what the next step is.
Oh, yeah, I'm going to say that.
You mentioned something there.
Yeah, so it's still very open what happens in higher dimensions. So dimension 3 or higher of when the one or so directors has real part equal to 0. So I've been working on different scenarios where that happens. So you could have some of the directors have positive real part, but some of them are 0, or all of them have real part 0. So there are a lot of different cases there.
But in connection with your last sort of examples there, so you've got examples of the point either way. Do you have some feeling which behavior is going to be more typical, or?
No, I'm not sure.
Okay.
Yeah. Yeah.
Is there a geometric or dynamical interpretation of what it means to have a director with real part positive? I'm just curious.
I guess I
Kind of.
like, I think about more like the equations there it's coming from.
Any other questions?
Yeah, so, sorry, I know I've asked you a lot about this already, but you mentioned this one three-dimensional example, and you said that you were able to show that you had orbits converge along a specific direction, but that you were trying to find whether or not it was conjugate to the translation. So just, I mean, if it's simple to explain, if not, don't worry about it. Like, what's different about this map? Like, you were able to show these other cases that you had conjugate to translation. Like, what ended up making this more difficult?
So when I get to the second step where I was solving some differential equations, the differential equation is a bit more complicated, and so I've been having trouble like seeing if I can bound it in the same way. So bound like our phi naught and phi 1 that we had there, if I can bound those in the same way where the results will work out.
Do you cover the Lorentz attractor in this?
Sorry?
Do you cover the Lorentz attractor in your three-dimensional examples? Or is that not tangent to the identity?
That's a flow, right?
Yeah, it's a flow. But
So you mean the time 1 map with a flow or something?
I don't know what I mean. That's the great thing about asking questions.
I guess no.
Well, but I mean, it's three-dimensional, it's got quadratic terms on the right in the differential equation. It's got 0, 0, 0 as a fixed point, I think.
That's a good question. Any other questions? All right, well, if not, then I guess everybody should leave except for the committee.